Sam Roberts here from Roberts Geospatial Engineering. Today I'm going to use ProRaster Scientific to answer a simple question, which is in 2022 in Pakistan, what is the area in square kilometres that was flooded in the Indus River Valley during the catastrophic floods of that year? So the question is prompted by a YouTube video that I came across from Minds Behind Maps. And in this video, they got three experts in the field, and they put this question to them and asked them to solve the problem using three different platforms. So the first was Google Earth Engine, the second is the Microsoft Planetary Computer, which is a similar kind of platform, and then the third is QGIS. So I thought I'd go through the same process, but using my software, which is ProRaster Scientific. So we're going to use Landsat data. So the first thing that I do is I go to Landsat Look and zoom into the area that I'm interested in. Here we are, Pakistan, and take a look at the scenes. So we just need to zoom in a bit further. So now it's loading our scenes. So here's the Indus River Valley, and you can see that these are the satellite paths going up this way. So the satellite's gone zoom up here and then zoom up here, and so I'm going to download this path 152 and this path 151 from row 43 up to row 40. So let's go to Earth Explorer. So make sure that you're logged in. Now, just so that you can see this, I'll move it over to this side. So firstly, I'm going to choose a date range. So let's go from June the 15th, 2022 to October the 31st, 2022. This is the area, the time range over which floods occur. Go to Data Set. Now I'm going to choose Landsat Collection 2. You have a choice between level 1, which is top of atmosphere, and level 2, which is bottom of atmosphere. On this occasion, I'm going to choose level 2, that's your bottom of atmosphere surface reflectance data, because I want to do an analysis. I'm not so interested in the visualization, so I don't need the high resolution panchromatic data. What I'm interested in is consistency between scenes, and in theory, the level 2 data will give you that. So I'm going to select Collection 2 Level 2 Surface Reflectance. Now we'll go to our additional criteria, and I'm going to choose the path 151 through to 152, and I'm going to choose rows 40 through to 43, and then I can get my results. So here's all of the previews of the scenes that you can download. So you hit the download button, and it comes up with this little dialog. So for ProRaster Scientific, when you download a Landsat scene, you want the whole thing. You don't want to go selecting this band or that band. You want to get the whole thing. So go to Product Options, drop this down, and in here you'll see the product bundle, 908 megabytes. So hit that button, and then that will begin downloading. The result that we get, if you go to your downloads folder, you'll get these tar files. So what we want to do now is decompress these tar files and extract them to an individual directory. So there's one tar file for each scene. So I have 7-zip installed, and I find this useful. So right click and go 7-zip, extract to */. So 7-zip runs, and now I have two folders, and in each folder you can see that have all the TIFF files for the different bands, and we have one per scene. So what I'll do then is I'll move these folders into the final place on disk where I want to store them, and then I can delete all the tar files because I won't be needing those again. So I have a directory here called Pakistan Flood. under my satellite directory, under my data directory. So here are all the scenes that I've downloaded. There's 48 of them, and each of the scenes is in its own directory. So now let's get into ProRaster Scientific. I'll bring that up, put that over here. So the first thing that we need to do is we need to register those scenes, and we're going to register them in a scene database. So go to the Browse Scene button and click down, and I'm going to say Add Scenes to a new database by folder search. So now I need to name my new scene database, so I'll call it Pack Flood 22. Hit OK. Now I'm going to browse to the folder where where I placed all of that satellite data. So there's the Pakistan flood folder, and here's all my scene folders. So select that. And now it's going to go through all of those folders. It's going to find the scene data in those folders. It's going to verify that that data is all there and as required. It's going to load all the metadata information and parse that. The metadata information will get stored into our little scene database. And in addition to that, we create a very special raster, one for every scene that we import. And this is called the Scene Assembly Virtual Raster. And from this point on, that is the thing that we're going to interact with in ProRaster Scientific. We will never interact with the individual TIFF files ever again. We won't touch them. They're going to be used, and we'll be drawing data from them all the time, but we're going to be working with this special raster, the Scene Assembly Virtual Raster. So our import has happened, and now we have this browser for the database, and we can zoom in on the map here, and here are the 48 scenes. So if I hover over this, you can see the names of the 3 scenes, plus it says there's 3 more in that location. And down here you have a spreadsheet with all the scenes, and you can see that I've downloaded data for 2021, and then I've downloaded data for 2022. So in 2021, you can see that it's all Landsat 8 because Landsat 9 was not available at that time. Whereas down here in 2022, when the flood is actually occurring, you can see that I've got Landsat 8 data as well as Landsat 9 data. So when you have 2 adjacent paths with 2 birds in the air, you'll find that a bird will survey one of the paths on one day, and the other bird will survey the adjacent path the very next day. So you're able to get data that's virtually contemporaneous along 2 adjacent paths. When there's only one bird, there'll be like an 8-day separation between surveying one path and surveying the next path. So that's our data, that's our starting point. Okay, so let's start to take a look at the data. I'm in my scene database, and I'll sort by acquisition time. Remember that I've got 8 scenes in each acquisition event. So let's select the first 8 scenes, and let's create a product. So I'm going to create a mosaic. So I'll right click and say create mosaic product. I need a new product database to put it in, so let's call that Pack Flood 22. Create scene mosaic. I'm going to order by cloud on land so that my cloudy data is overprinted by my less cloudy data. Hit OK. And it comes straight up with the product editor. So here's my mosaic. We can look in the preview. Yes, we've got some data. So let's render this now. We can choose our spectral target. We've got digital numbers, and the scene assembly raster has applied the transformation factors to those digital numbers to turn them into reflectance and temperature. And we're going to choose reflectance, and it always chooses that more processed level of data by default. and we'll choose natural color and we'll hit OK. So here we are in ProRaster, and you can see that we have a bit of cloud down the lower end of the valley. Here's the Indus Valley. This is 2021. This is prior to the flooding, so this is in a sort of dry time. So that's fine. We've validated that we're looking at the right data. Let's now go into the product wizard, and we're going to create a mosaic sequence for all the data that we've acquired. So I'm going to need the tile IDs. I can get them from here. I'll just right click and use tile ID to clipboard. Now go to the create product sequence wizard. So I'm going to add a new one. I'm going to call this the Pack Flood 22 number 1. I'm going to target this product database that we just created. Choosing a platform, there's only one option in this because it's queried the database and found out what we have, so we don't need to change anything there. I'm going to create a mosaic sequence. I need those tile IDs. I just copied them, so I'll paste it into there. There's the tile IDs that I want in my mosaic. And we're going to order by cloud on land. Hit next. Now I want it to automatically identify these 6 acquisition events that I have. Now the later events happen over a period of 2 days, but the earlier events happen over a period of about 8 days. So if I put in 10 days, you can see that it says we have 6 acquisition events now. So we're going to create a sequence by acquisition. I'll use the latest time. We're going to bring scenes into it by acquisition, and we'll just use the central acquisition. That's all fine. Hit next. It's going to go into that database. It's generating the product. Let's just look at the report that it's created. So a total of 48 scenes have been included, a total of 6 acquisition events, and in each of those events I've allocated a total of 8 scenes. That's exactly what we want. Hit OK. I'm going to go now into edit product. So here's our mosaic sequence. Let's close that one out. And we'll simply render now. We'll choose, let's say, choose natural color with atmospheric removal. Hit OK. Let's bring that over here. Zoom in a little bit. So let's go to the time control panel. So you can see now that I have 6 time points. So from June 30th, 2021, prior to the flood, to October the 29th, 2021. This is a normal year where we're seeing a certain amount of flooding. Then June 2022, prior to the flood, or really at the beginning of the flood, you can see that it's starting to get flood water coming down the river. July 2022, now we've got a significant amount of flooding starting to occur. September 2022, and you can see all this flooding in here and out here, and this is where all the damage was done. Probably the peak of flooding was in August, in the month prior, but all the satellite scenes from August are very cloudy, perhaps not surprising because it's raining cats and dogs, and September is probably post the worst of the flooding, and then we have October the 24th, and you can see some flooding in that at that time as well. So that's our sequence of mosaics. So the first step in our analysis would usually be to remove clouds. So let's go back to the product that we created with the product wizard. So here it is, it's our mosaic sequence. Let's render that mosaic sequence. I'll use this band combination, natural color with atmospheric removal. Hit OK. So you can see there's some cloud down here, but then other scenes look relatively clear. Let's bring this over here so we can see more. I'm just going to mask out now the cloud. So I'm going to go to the mask component, choose the raster source. I'm going to go to the mask field, and we'll say pixels clear. Now, sorry, let me then enable that. Okay, so I've zoomed into this area, and you can see that we've got a lot of grey here now. So if I just turn that mask off, we've got river. Turn that mask on, we've got grey. So the QA data is identifying pixels along the river as being cloud. So we can investigate this a little bit more closely. So I'll zoom in. Come into my algorithm. I'll add a lookup table color layer. We'll choose the mosaic sequence. We'll go to the QA pixel values, and we'll just see what we're looking at. So we usually have values of 0 or 1. So let me bring up the key data value. So this is 0. If I turn that off, this is what we're looking at. So fill is 0, so that's fine. Dilated cloud. Okay, so here you can start to see the problem. It's identified all this dilated cloud where the river is, where I don't think there's any cloud at all. Go to cirrus. It hasn't identified cirrus. Go to cloud. It's identified cloud, but in this case, I would say that the cloud that it's identified is actually water. Let's take that mask out. Turn this back on. You know, this is water, not cloud. Cloud shadow. Again, lots of cloud shadow. If we go to cloud confidence, so this is its cloud confidence, and and it's reporting values of 3, so it's confident that this is actually cloud. Whereas I would say it's not cloud, it's just water. So I think that's a bit problematic. So it's the QA data is working across most of the data set, but in some of the time points, it's incorrectly identifying the floodwater itself as cloud. So I'd say to the USGS and to the European Space Agency, if you just want to do one thing to improve the usefulness of the Earth observation data, Sentinel-2, Landsat, is improve these QA masks if you can to accurately identify land, water, snow and ice, and cloud. So I've decided in this analysis, because of the weaknesses in that QA data, that I'm not going to filter out the cloud. Now, I downloaded scenes that were already largely cloud-free, so I'm just going to use that data without masking out the cloud. So I'm back to my mosaic sequence product. I've decided I'm not going to mask out the cloud, but I am going to clip to a polygon of Pakistan, and I've acquired this from Natural Earth website. So hit clip by polygon. In all these operations, you don't need to set the input and the output. It's all set for you. But you do need to select your polygon, which you can either browse to, or as I've used it before, it's in the list. So Pakistan, hit OK. So now I have a a new level in my tree. So let's render this now in the standard way. And you can see that we've now taken a big bite out of the side here. That's India. And we've clipped out this area down at the south. It's clipped out the ocean to a certain extent. And so I've clipped to Pakistan. Now let's compute the NDWI water index. So go to Index. I'm going to compute it from bottom of atmosphere reflectance. I can choose any one of these standard indices, or I can come down here and choose from about 200 odd indexes down here, and you can choose as many as you want, or just one. So let's come in here and just choose NDWI. Normalized difference water index green minus near on green plus near. Hit OK. Now we can display this. The standard indexes have color tables shipped with the product. So if you come into the color layer here, color page, you can see that it's chosen the NDWI data transform and the NDWI system map. So what we're seeing here is blue, where it's above 0.1, and then these green and orange colors, which indicate that it's not water. So this is water and this is not water. And you can see this transition around here is around 0.1, where it goes to classify as water. So we have to choose a cutoff, and it's usually around 0.1, but let's see what happens when we do that. So let's come in here and we'll put in a clipping range from 0.1. So everything above that is going to be water. Everything below that, we'll say it's not water, so we'll clip that out. So let's say clip below the minimum. And this is what we get. So you can see that these areas that are flooded are all covered, are all identified. But we lose a lot of the river itself. A lot of the river is actually giving us different values, and it's not being identified as water with that cutoff value. Which is interesting. So if you just use standard NDWI, you may miss out on quite a lot of the actual flooded pixels. Now there are other indices, of course, and you can play around with them. We can compute as many as we want and see if other indices perform better. But what I did was, let's get rid of that. I went back to, let's just go back to this one. We'll go render now. And I started playing around with the band combinations. And the ones that I found that really worked well were false color urban, geology, and bare earth. Now these ones use SWIR 2, SWIR 1, and either the red, green, or blue channels. So let's take a look at that. So this one's SWIR 2, SWIR 1, red. I think that's right. Let's see. Yeah, band 4 is red. So now we have darker values identifying water and lighter values identifying everything else. So you can see the river comes up quite nicely, and these flooded areas and these areas that have not been flooded are quite different colour. And I played around with this and I eventually chose coastal aerosol as for the blue band. And you can see that there's a real contrast between the water areas that are flooded and everywhere else which is not underwater. So we've got SWIR 2, SWIR 1 and coastal aerosol as our target bands. So I decided to make my own index from those 3 spectral bands to get some kind of improved measure of what is water and what isn't. So let's come back to here, back to our product editor. Go to our Pakistan clip. Now I'm going to use a calculator expression. So I want the bottom of atmosphere reflectance. So we'll do SWIR 2. So put that one in, plus SWIR 1. Put that one in, plus coastal. And we'll just divide by 3 because we have 3 bands. Hit OK. Let's render this now. Bring this one over here. So what I want to do is find out what value is the transition point from water, which is basically represented as blue here, through to land. So we'll look at this edge, and you can see that it's somewhere around 0.05. I decided to go with 0.05, 0.06, where we see a transition from water to land, and going over to the river, you can see the values in the river are consistently less than 0.05 and 0.06, so that seems like a good choice. So if we come into here and say, go to our color, just do a linear transform with a manual clip and go from we go from minus 100 to 0.05, and we clip above the maximum. Sorry, minus 0.5. It doesn't matter. Anyway, so now we've got red here identifying, well, let's just reverse the color table so it's blue. So now we have blue, everything below 0.05, and these are the pixels that I'm suggesting are flooded pixels, and that everything that is not below 0.05 is a land pixel. So now I want to count the pixels in this raster that have a value of less than, say, 0.05. And I could add another calculator expression to do that, but we can probably just edit this expression. So instead of this, we'll just say, so condition. If that is less than 0.05, then we'll output 1, otherwise we'll output null. Hit OK. If I preview this now, you'll see that I've only got now the water retained as pixels with a value of 1. Now I can compute statistics. So let's hit OK, and that's going to compute statistics. Now remember that we've got a mosaic sequence. So we have 6 mosaics in this sequence, and all of this processing is being applied to all of those mosaics. So what we're computing now is a multi-dimensional statistics, in other words a temporal statistics, so we're going to get statistics for each one of those 6 mosaics in the sequence, and then we're going to be able to compare data from prior to the flood and then during the flood. So that will take just a little while to compute. Okay, so those statistics have computed. I had enough time to go out and have some pineapple while we were waiting. And so here's our statistics. We go to the summary, you can see it's counted the number of valid cells. If we go to spatial, it'll tell you what the cell size is. So we computed it at base resolution at 30 meter cell size, the native resolution of the Landsat satellite. And it will tell us the area that is represented by those pixels. And I should just make the point at this, make the point that you do need to make sure that it's in an appropriate coordinate system. So it's currently in a UTM coordinate system, zone 42, which is fine. But once you start putting mosaics together, at some point the system will decide that if you've got too much east to west data, then it'll step away from using a UTM coordinate system and go to a geographic coordinate system. At that point, your cells are in degrees, not meters, and so you need to be aware of that and make sure that you're choosing an appropriate coordinate system in order to compute areas. Now, here's our dimensions. So if we go to September 22, which is during the flood, you can see that we've got a big number here. So that's 24,180 square kilometers that are underwater at that time. And I suppose if we go back to the initial, this one, which is a normal flood, in a normal flood you've got, let me take that out, so 8,667 square kilometers, so a difference of about 16,000 square kilometers. Now, just not 100% happy with this, because down in the south where we've got the where the delta is, I think we're picking up a lot of seawater as flood area, and I don't think that's appropriate. So I'll just show you one other thing, and that so now I'm going to mask the data using a digital terrain raster. So I have a global terrain raster, so this one, it's Merit DEM. So this is global data, and if we zoom in here to Pakistan, this is a 90 meter resolution or 3 arc-second resolution data. So I'm going to clip out a lot of this area. I'm going to clip everything that's below 5 meters RL. So firstly, I'm going to take my global data set and I'm going to clip it to my Pakistan polygon. So let's go into processing menu, clip to polygon. Merit is my raster source. I'm going to output it to temp. I'm going to make this Pakistan DM. And we're going to clip to Pakistan, hit OK. It'll immediately open that, and here's my clipped Pakistan DM. Alright, so go back into the product editor. So I've clipped it to Pakistan. Now I'm going to do a well, what I can do in fact is I can just go into this calculator and modify it further. So I'll come in here and I'll load up my Pakistan DEM. So that now appears in my list as B00, that's a variable that I can use. So I can put in here condition. So if B00 is greater than 5 meters and I add up my SWIR 2, my SWIR 1 and my coastal aerosol and it's less than 0.05, then I'm going to output 1, otherwise I'm going to output null. So hit OK, and you'll see that it started computing statistics again because I've updated this item in the operation cascade, and so now it's updating all the other operations below it, including that statistics. But let's not do that yet. So we'll just go into here, into our preview, and then down here you can see that where we had a lot of data previously, we've now clipped this out and clipped it back to 5 meters in RL, and so some of that information that telling us that it's flooded, but really it's just delta, has been taken out of that data set. So we can recompute statistics, and I can come in here now and hit execute operation to recompute those statistics, and we'll get an updated. So let me just review the results that I computed before. So using this technique, clipping clipping to 0.06, I found that the difference in the flooded area between October 2021 and September 2022 was 19,801 square kilometres. And if you reduce that threshold, it drops down. And with NDWI, with a threshold of 0.1, I found that there was only a difference of 7,800. Now, one of the flaws in this analysis is that we're looking at one particular time point, but a flood isn't static. It moves. So we need to look at multiple time points to track the flood as it comes from the north down to the south. So I'm not going to take you through that, but the technique that you need to use is to, if we're computing our little pseudo water index, we know that we're looking for low values. So we can compute it for the different mosaics and use the calculator to choose the minimum value of those multiple different mosaics that we have. So that kind of accumulates the minimum values, so we'll end up with more water being tracked. So I did that. So I used the minimum values for both June and October in 2021, clipped to 0.05, and I got 4,459 square kilometres. And then for 2022, I used the minimum values of both September and October and got 22,100 square kilometres. So our difference there is 17,640 square kilometres. That's for a cut-off value of 0.05. If I went to 0.06, it'd be slightly bigger. So I think that is absolutely a minimum value or a minimum estimate for the flooded area, and the true value is probably higher, perhaps around higher than, say, 20,000 square kilometres, which is substantially lower, I might point out, than the 75,000 square kilometre estimate that you'll find on Wikipedia. I think that's probably not valid. I think it's going to be more like around 25,000 or less. So that is how to use ProRaster Scientific to compute that value. ProRaster Scientific is a bit like QGIS. So you start off by downloading the scenes that you want from your provider, USGS, or from the European Space Agency or wherever else. And then you, having acquired that data and storing it on your local hard disk, then you do your processing. Microsoft Planetary Engine and Google Earth Engine, of course, you don't ever acquire the data. They have the data on the servers, and then in order to do the analysis, you have to program their servers, and that's the big difference. ProRaster Scientific doesn't require you to be a programmer. You just have to learn how to operate the software. I'm losing my voice. So thanks for watching, and see you next time at Roberts Geospatial Engineering.